So at a high level, the hardware we need to implement our network must be capable of producing, transmitting, manipulating, and measuring quantum data in the form of qubits. In some networks, we'll also need the ability to store quantum data if we need to wait for a message to cross the network before it can be used. Now, for quantum networks, a lot of this hardware will be geared towards qubits in the form of photons, or particles of light. And qubits are very sensitive to external noise. So not only do we need hardware that's capable of doing these things, producing, transmitting, manipulating, storing, and measuring, but the hardware also needs to be able to do these things well enough to meet the requirements of our network. There's a notion of quality of quantum data, which is referred to as fidelity, and a higher fidelity means higher quality data. And so we need to make sure that whatever hardware we're using doesn't reduce the quality of our data too much, or the network really won't be usable. Some additional requirements that should have been investigated during design emulation include that our hardware produces some known quantum data, it supports the necessary operations and measurements needed to implement our algorithms and applications, and they satisfy any storage requirements for our protocols and applications. So starting off with this first item, if we're using a photon source for generating entangled pairs of photons, then it's necessary to know the specific kind of entanglement that the photons will be carrying. Otherwise, the network won't be able to confidently claim what kind of quantum information is being distributed between the nodes in the network. This is necessary as many algorithms and protocols depend on knowing what kind of quantum data is being processed for them to work properly. Once we know what kind of quantum information we're starting with, we can then use our hardware components to manipulate this data and extract the information we want using measurements. And as I mentioned before, since we'll be exchanging classical messages as part of our applications and protocols, we need to be able to faithfully store this data while we wait. So in addition to these kinds of requirements, which are more oriented towards the primary quantum devices that realize the network, there's some more hardware requirements that also need to be met. So as I mentioned a few times, we need the ability to send classical messages between nodes in the network, and so we need classical networking infrastructure in addition to the quantum hardware. The network needs to enable communication between the relevant nodes in the quantum network, and should observe low latency to respect the storage constraints imposed by our quantum hardware. Next, we need to make sure that we have any additional auxiliary hardware components that might be required. So in design emulation, we may not have fully captured all the practical aspects of deploying and connecting the devices. And so hardware vendors can provide input and recommendations for supplementary components that will allow the hardware to operate as expected or further improve its performance. This is especially helpful when an organization is just starting out and doesn't have intimate experience with the hardware internally. Then we also need to make sure that our selected hardware is compatible with our software. This includes being able to use our software to configure the device, or being able to issue instructions to the device, such as a quantum gate or a measurement if we're processing qubits. And we need to be able to talk to the device at a low level, as coordinating usage of quantum data across the network requires rapid and dynamic control of the devices if we want to make the network high performant. Oftentimes, these hardware components might be packaged with some additional software like graphical user interfaces, which are helpful for running experiments in a lab, but this type of software isn't sufficient for the kind of control we need in a large-scale network. You can imagine it wouldn't be nice if we had to have a lot of people sitting at these types of graphical user interfaces controlling each individual component of the network, and I mean, that doesn't really sound so nice. So now, in addition to the actual hardware itself, we need experienced individuals capable of deploying the hardware. So whether you're doing an initial verification of your hardware or performing the installation, it's necessary to have the appropriate experience to do so. Individuals that have experience handling and transporting the hardware are necessary to make sure that components are moved between physical locations without damaging the equipment. So for example, if you have some very sensitive optical components that are used in the network, it's important to shield these components from bright light that could damage them. It would be a shame to finally get our hands on some expensive hardware after waiting a long time just for us to break it due to mishandling. We also need experience in installation and troubleshooting of the various hardware components. So hardware components need to be connected to one another correctly to make sure that devices operate as expected. And so we need individuals that can do so and easily identify when such connections have been made incorrectly. Now, last but not least, there needs to be experience with environmental factors that may not have been modeled in design and emulation. These factors can include external sources of noise, like mechanical vibrations or stray electromagnetic fields that are specific to the location you want to deploy the pilot network. The hardware deployment must ensure that such external factors are accounted for and have their effects on the devices reduced so that the performance of the pilot network closely aligns with what is anticipated from design and emulation. So in this case, we might need to introduce some electromagnetic shielding or vibrational damping to the site where the hardware is being deployed. The key to success in all of these cases will be collaboration with hardware vendors. Vendors know their equipment best, so establishing good communication habits with them will greatly benefit your own deployments. Vendors can provide hardware documentation, knowledge of best practices, and potentially even training to help build the internal familiarity and experience that will be necessary for long-term support of the network.